It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, welcome to Unit 3 here, where we're going to start by looking at rational expressions. So this unit kind of has three pieces to it. The first thing we're going to deal with are fractions, which are rational expressions. So that's kind of the first week of this unit. So let's start by just getting our brain thinking about rational numbers and fractions. So write two fractions that are equivalent to 1/3. So what are two numbers that are equivalent to 1/3? Well, 2/6 is. Why? Because that's times 2 on the top times 2 on the bottom. I don't know, 10/30 is, because that's times 10 on the top times 10 on the bottom. I can generate any equivalent ratio by multiplying by some number. As long as I multiply that number on the top and the bottom, I'm going to create an equivalent ratio, an equivalent fraction. So that's what rational numbers are all about. Today we're going to be dealing with equivalence and how do I know if two fractions are actually equal. And it comes to this idea of if I want them to be equivalent, I need to multiply both the numerator and the denominator by that same value. So again, rational numbers are fractions. Rational numbers are fractions. So let's go through here and talk about which of these are rational numbers. 3/4 definitely is good to go. 3.14, not pi, just the number 3.14, is actually 314 hundredths. That is a rational number because that decimal terminates. Pi is the classic example of an irrational number. Pi never ends, never repeats. It's a weird, irrational number. Pi is irrational. It's a real number. It's not like the i's. Those are completely separate numbers. It's irrational. This is no good. If I have 5 friends and divide my cookies up between, if I have 5 cookies divided between my 0 friends, that's not a thing. You cannot divide by 0. Dividing by 0 is no good. And that's going to continue to be the whole theme of this week. This is a real number because that negative's outside. It's not inside. But I need to deal with the square root of 17. I need to deal with the square root of 17 there. So this is irrational. 17 is not a perfect square. 17 is not a perfect square, so that makes it irrational. This looks like a fraction. But you've got that sneaky irrational number of the square root of 5 there, which makes the whole thing irrational. -1, well, that's a fraction. -1 over 1, that's good. And 0 over 1, that's good. You can have 0 up top. You cannot have 0 in your denominator. So what are rational numbers now that we kind of played around with them? Rational numbers are the ratio of two integers. The ratio of two integers, a over b, where b cannot equal 0. So a and b are integers. Those are your nice counting numbers, and they're negatives. And b is also an integer, but it can't be 0. So let's talk about rational expressions. We dealt with rational numbers all the way since 6th grade, or 5th grade even. Now let's talk about rational expressions, which are the Algebra 2 version of those rational numbers. So it's a rational expression is in the form, it's a ratio, a fraction of two polynomials. So we're taking our polynomial functions from earlier. It's the ratio of two polynomials, p over q, where q cannot equal 0. So it's the ratio of p over q, one polynomial over another polynomial, where q of x can't be 0. Your denominator cannot be 0. We call those values where the denominator equals 0. Those values are what make me undefined. So what are some examples? I don't know. 2x plus 7 over x squared plus 1. 5x cubed plus 7x squared plus 2 over x. That's a rational expression because it's a ratio of two integers. What else is there? 7. 7 is actually a polynomial. It's 7 over 1. I don't know. 2x. Polynomials are also rational because they're over 1. Non-examples is you cannot have 0 in your denominator. You cannot have 2x plus 7 over 0. That's not a rational expression because your denominator is 0. I mean, it's got to be polynomials up there, and we haven't encountered like 3 to the x over x. That's an exponential function. That's no good. We haven't encountered a lot of non-polynomial functions, but it's got to be polynomials in our fractions there. So let's get to it. For what values of x is this rational expression undefined? Well, undefined means I'm going to look at the denominator, and I want to know when is the denominator equal to 0. We're going to solve this. When does my denominator, what values do I have to throw out? Because that makes me undefined. That means when I plug it in, the denominator spits out a 0. So I've got to solve this equation here. What multiplies to negative 12 that adds to negative 4? Minus 6 and positive 2. So x equals 6 or x equals negative 2. Those are what make me undefined. We throw those values out. I can plug in any number I want to this fraction here, but I can't plug in a 6 and I can't plug in a negative 2. How do I simplify this? Well, when we simplify rational expressions, we're going to factor them. To simplify a rational expression, we're going to factor them. And you thought factoring was going away. It didn't. So let's look up at the top. The top there, it looks like I have some difference of perfect squares. And on the bottom, well, the bottom I already factored that. What multiplies to negative 12 that adds to negative 4? Well, that would be negative 6 and positive 2. Now that it's factored, we can divide out common factors. You can't just start slashing stuff out in the beginning. That's really, really bad. You can't start dividing out common factors until it's factored. So we can divide out that common factor of x minus 6, and this expression simplifies down to x plus 6 over x plus 2. You can't clean it up anymore. That's it. X plus 6 over x plus 2 is really the same thing as that expression up there. Those two expressions look different, but they're really the same thing. So for these problems here, we're going to reduce them to simplest terms and identify what makes me undefined. So really what we're going to do here is we're just going to start factoring. Let's just start factoring these expressions piece by piece. Let's deal with the top there. What multiplies to negative 6 that adds to negative 1? Go negative 3 and positive 2. And then the bottom, it's not a trinomial. I should always look for a GCF. I remember that GCF's x plus 2. So I factored it. What makes me undefined? Let's start with that. When is my denominator 0? Well, what x equals negative 2? We got to throw that one out. And when is 5x 0? 0. I got to throw out those two numbers. Those make me undefined. When I plug in a 2 and when I plug in a 0, those values are not allowed to be plugged in for this fraction. And then I'm going to slash out that common factor. Goodbye. And I'm left with x minus 3 over 5x. That's my simplest form. So our game plan is to factor and cross out common factors. That's all we're going to do here to create an equivalent expression. All right, I got a trinomial up top here. Ooh. All right, I got to AC this here. What multiplies to negative 6 that adds to negative 5? What multiplies to negative 6 that adds to negative 5? Negative 6 and 1. So let's split the middleman because I got an AC method this here. I got a negative 3x. There's a tough one with that negative out front there. It throws everything off. So I get x plus 2 and negative 3x plus 1 as my factors. So that's the top of this fraction. The bottom of this fraction, what do we got here? Looks like perfect cubes. It's not. I think it's just a GCF. Just a GCF. So I really have x plus 2 over negative 3x plus 1 divided by x squared times x plus 2. So let's deal with undefined. When am I undefined? Let's focus on the bottom. Well, x can't be 0, or x cannot be negative 2. Those make me undefined. And I'm going to slash out my common factor to simplify that expression all the way down to just that. Instead of plugging in something up there, I'd rather much rather just plug a number into here to compute that expression. So this expression is equivalent to the original one. And these are what make me undefined. Sliding. All right. Not much I can do up there. That looks like difference of squares to me. X plus 3, x minus 3. So when am I undefined? X cannot equal negative 3, x cannot equal positive 3. Those are my values that make me undefined. We're going to throw them out and say you can't plug those numbers in. Now, this looks really tempting to cross out here, but they're not the same thing. Watch what we need to do here. They do kind of divide each other out, but I've got to take out a negative 1 there. Because look what happens is that lets me use the commutative property. By taking out a factor of negative 1, that lets me use the commutative property. So when you're dealing with these 3 minus x, x minus 3, they do divide each other out, but what's left behind is a factor of negative 1. So they do divide each other out, but they don't divide to 1. They're leaving behind a factor of negative 1. And that's only with the subtraction ones when they're backwards. That's only with the subtraction ones when they're backwards. Oh, we're going to skip this one. Yeah, we're going to skip this one because we can. Because we can, we're going to skip that one. All right, here we go. Last thing, and then I'll end the video. For each of these rational expressions, state me a common denominator. So we're going to go back to like 3rd grade here and 4th grade and talk about common denominators. So we're going to create a rational expression so that everyone has a common denominator. Well, let's deal with fractions first. If I had 2/5 and 3/4, and let's throw in a 1/2. I need to get a common denominator between all of these. I need to find my least common multiple. Everybody needs to have a factor of 5, a factor of 4. I don't really need a factor of 2 because that's already in that 4 there. So my least common denominator here would be 20. What do I do to everyone to make them have a denominator of 20? Well, if I need to make this 20, I need to do times 4. But if I multiply the bottom, I also have to multiply the top. Here I need to do a times 5. I'm going to do top and bottom. Here I need to do a times 10. So I'm going to do a top and bottom. So when we get a least common denominator, everyone's got to have the same factors in the bottom. We have to make sure everyone's got all the factors that they need in the bottom. And then we multiply the top and bottom to make the equivalent expressions. So I've got 8/20, 15/20, and 10/20. Now I can compare those fractions. Same thing when we deal with these rational expressions. Everybody needs a factor of x minus 2. And then wait a minute. I think I can GCF there. This already has a factor of x minus 2. It has a 4. So over here, I'm going to stick in a 4, but I also have to multiply the top by 4. So now these expressions have a common denominator. When we deal with rational expressions, we always want to factor the denominator because that tells us when things are undefined. In this case, I'd throw out a 2. X cannot equal 2. And it lets us see what we need, what factors we need for a common denominator. Here, everyone needs a factor of x plus 2, and everyone needs a factor of x minus 5. I can't add or subtract, so all we're going to do is say, all right, I got the x minus 2, it needs an x minus 5. If I put an x minus 5 on the bottom, I've got to put it up top as well. Over here, I've got the x minus 5, I need the x plus 2. So I'm going to stick it in the denominator, which means I also need to put one of those factors up top in the numerator. And then if I wanted to, I could distribute up top. Leave these factored. You always want your denominators factored. Distribute again. Leave these factored. Don't go making more work for yourself. But the key idea is sometimes you just flip-flop the factors. All right, I need an x minus 5. Let me put that on the top and bottom. I need an x plus 2. Let me put that on the top and bottom. This is the one that gets everybody because they just want to add a plus 3 there and a plus 3. Well, if I had 1/2 and I go plus 3, does that create an equivalent fraction? Is 1/2 the same as 4/5? No, we can only accomplish this by multiplying. So actually, everyone needs an r plus 3, and everyone needs another factor of r. So I've got r plus 3 here. I'm going to stick in a factor of r. Put it on the bottom, got to put it on the top. I need a factor of r plus 3, so let me put that up top. And that's it. I've created equivalent ratios for r squared. I'm going to just flip that around on the bottom there. I'm going to distribute here 5r plus 15 over r plus 3. And again, undefined. When am I undefined? I'm undefined at -3 and 0. I can't be 0 as well because I have that plain old r. Don't just try to add it. Just kind of flip-flop them. Everyone needs an r. Everyone needs an r plus 3. Ooh, nice. So everyone needs an x plus 3, an x minus 4, and everyone needs this thing, but wait a second. What is that thing? What multiplies to 12 that adds to -1? What multiplies to 12, -12, that adds to -1? Well, that would be -4 and +3. Oh, so this fraction's good to go. We're not going to touch that fraction because it's got the common denominator. It's these first two that need to get fixed up. This first fraction needs an x minus 4, so I'm going to put it on the top and bottom. This next fraction needs the x plus 3. So I'm going to put it on the top and the bottom. And that's that. We're going to be doing this all week of getting common denominators. If you put a factor in the denominator, you also have to put that factor in the numerator. And that's it, folks. I'll see you in the next lesson.